Hello everyone, this is the video submission accompanying the paper Value Functions are Control Barrier Functions, Verification of Safe Policies Using Control Theory. Many applications in robotics are safety critical, such as human-robot teaming, autonomous driving, and general-purpose household robotics. Thus, there is a significant need for control algorithms capable of solving such complex problems while having verifiable safety guarantees. Reinforcement learning methods, although highly general and scalable to diverse tasks and settings, are difficult to verify due to their black box nature. In comparison, traditional methods based on control theory, such as the method of Lyapunov functions, promise strong verification guarantees, but were historically difficult to use outside of toy systems as they required manual design based on domain expertise. To remedy this gap, a promising idea is to combine the strengths of learning-based and control-theoretic approaches by imbuing learnable functions with the verification properties of certificate functions. There are many such types of functions, each of which verifies a different type of behavior. Previous work on this topic has sought to achieve this goal by attempting to make existing control-theoretic approaches more scalable. For example, by introducing learnable functions and self-supervised regularization losses to ensure certificate properties are satisfied. The limitation of such work is that it fails to achieve the full scalability of RL-based methods, as existing works require prior knowledge of system dynamics and thus fail to extrapolate to more complex systems where dynamics cannot be modeled analytically. In contrast, our approach starts from the RL perspective and attempts to improve verifiability by leveraging ideas from control theory. Our approach thus benefits from retaining the full scalability of RL-based methods at the cost of having weaker verification guarantees. In this paper, we present theorems connecting value functions and control barrier functions. We then devise an RL-based method to learn control barrier functions on black box systems. We additionally propose metrics for analyzing learned CBFs, as well as implementation details that resulted in better CBFs. Before introducing control barrier functions, we first provide some motivating analysis. Given the state space X, we define a set of safety violations X unsafe. This then induces irrecoverable states X irrecoverable, as well as safe states X safe. A control barrier function certifies a subset of the safe state space denoted by X safe H. A control barrier function is a mapping from the state space to a real value. It is constructed such that if the value is above a certain safety threshold, then the state is guaranteed to be safe. A more formal definition and proof is provided in our paper. We now consider value functions which also map states to real numbers. Considering the following task structure, where the reward is 0 if the state is unsafe and 1 if it is safe. Furthermore, we assume early termination on unsafe states. It turns out that the value function for this task has a similar structure to a control barrier function, where if the value is above a certain safety threshold, then the state is safe. Motivated by this analysis, we propose our main theorem linking control barrier functions to value functions. Namely, a control barrier function h is equal to can be defined by taking the value function v and subtracting a constant r, defined in our paper. This allows us to interpret the value function as a control barrier function and then verify the value function v satisfies CBF properties. We now propose our RL-based method for learning CBFs. Concretely, we train any architecture, such as deep queue networks on any environment, cart pull, with the safety-preserving task structure, in this case, to stabilize the pull at an upright angle. Based on control barrier function properties, we propose novel metrics for verifying learned value functions. Firstly, validity, which measures the size of the region in which the learned CBF satisfies CBF properties. Secondly, coverage, which measures the size of the safe region certified by the learned CBF. We also propose 3 implementation details aimed at improving these metrics. Firstly, to bound the range of the value function using a sigmoid, which we find to stabilize the learning signal. Secondly, to supervise the value function over X unsafe, which we find provides a helpful auxiliary learning signal. Lastly, we find that improved exploration, it helps to increase the size of the safe set certified by this control barrier function. We performed 25 total training runs of 5 seeds across 5 experimental settings, ablating each of our design choices. As the main purpose of a CBF is to act as a safety constraint, the main metric we consider is the safety constraint episode return. We find that our proposed implementations details are critical to achieving good performance. To visualize safety performance more clearly, we plot the safety constraint episode length over 100 trials, as well as the safety success rate, defined as the fraction of episodes with no safety violations. The architectures with higher validity show clear differences in the capacity to serve as safety constraints. We find that for the best model variant, the safety constraint policy rollout is capable of maintaining safety while traversing both extremes of the state space. Lastly, we visualize a typical learned CBF for each experimental setting by plotting the values across the state space. We find that our proposed implementation details enable learning of a certified safe set that is both correct in terms of not overlapping with the safety violations, as well as being large in that it has the maximum possible area. We now discuss our work in relation to existing work. Firstly, compared to the bulk of existing work on certificate learning, our work offers unique advantages in that it does not require analytic system knowledge to learn a control barrier function. Secondly, in the context of safe RL, which assumes safety constraints are known a priori, our work is orthogonal and complementary as we provide a method to learn a safety constraint, which can then be used in safe RL methods. Our method does have some limitations. Firstly, in our RL-based method, there are necessarily safety violations during exploration, as that is the only way to learn about safety in the absence of dynamics knowledge. Secondly, our method suffers from relatively loose verification guarantees, as the sampling-based metrics we use are only a statistical argument. While stronger verification methods have been reported in control theory literature, these require system knowledge to implement. Overall, the question of how best to incorporate existing knowledge into the RL-based framework is an exciting future direction. One possible method is to pre-train with nominal system models and then fine-tune the resulting CBFs with RL to adapt them. In addition, we see our RL-based method as being especially suited for learning CBFs from perceptual feedback, such as visual input. This would be difficult using existing certificate learning methods which have to analytically model dynamics. To summarize, we have contributed theory, methods, metrics, and practical implementation details for learning certificate functions. Overall, our work represents a significant step towards scalable and verifiable control methods for safety-critical applications. Thank you.